Institute of Engineering and Technology.
Hello students, after defining multiple integrations for double integration, also going through the basic properties of double integration like how to solve it for Cartesian coordinates as well as how to solve it in case of polar coordinates. Today we are going to consider more generalized form of multiple integration, which is in three-dimensional space, the space in which we are all living. Three-dimensional space in Cartesian coordinate will be considered today in our discussion. So basically we are going to consider four parts in this talk. The first part is how we can format this triple integration with help of x, y and z coordinate. What do we mean by this triple integration graphically? We'll see its graphical interpretation. We'll also go through one example in which we will solve triple integration to find volume of a solid, which is a random solid in three-dimensional space. Also at last, we'll consider how to solve triple integration for any random surface. So today's talk is all about triple integration in Cartesian coordinates. So let us start our first part, that is triple integration and its formation. So if I consider triple integration, then basically in formation I should consider three integrations over a function which is considered for dv. Now these three integrations are defined on some domain which is given by d in a three-dimensional space, and it is taken over dv. dv means volume element. Now let me recall at this point, whenever we are taking single integration, integration is integration of f of x with respect to dx. What does it mean? It simply means that we are considering x directional change in the integration, and then correspondingly if we are considering integration for function of one variable, we are finding actually area. What is happening in two-dimensional integration? When suppose I take double integration over f of xy dx dy, ultimately you will receive the volume. So now at this point, if you are taking triple integration of the function, and if the function is not equal to 1, what actually it will give you a hypervolume, a volume which is actually in a four-dimensional space which we cannot imagine, as we all are three-dimensional beings. So this is our restriction, and this is the reason why in most of the cases you are going to use single as well as double integration. Use of triple integration will be whenever your function is equal to 1 to find the volume. Now let us consider how actually we are going to consider this three-dimensional integration. We need to consider first of all that there are two components in this integration. There is a first component d and second component dv. To understand this, let me consider first of all what do we mean by this capital D. Now if you are taking function of one variable, your input is coming from one dimension only, that means x-axis. If you are taking integration with respect to two variables, your input is coming from two-dimensional plane. But now if you are considering triple integration, obviously your input will come from three-dimensional space. So this D, which is like a lump of clay in the three-dimensional space, this is nothing but our input. So that means now we are selecting points from this particular chunk of three-dimensional space, and then we are considering all inputs from this chunk to the function f of xyz, and then we are recognizing what actually is our final answer. So now the process is like this. Suppose I consider a random point which is denoted by xk, yk and zk from this domain D. And now if I find its surrounding, then obviously its surrounding will be a cube, and that cube is nothing but delta xk delta yk into delta zk. So that volume element is nothing but dv. So actually we are taking dx into dy into dz. This order can be in any random way, but ultimately multiplication will give you answer of dv. So this indicates that our input is coming from 3D and our output is going into the fourth dimensional space. So the physical interpretation of last value of this integration is nothing but the hypervolume. Now let us come to the second part, how to distribute the value of dx, dy and dz. Suppose I consider for simplicity dz, dy, dx as my order of integration. Then how the values of integration will be. So I am following the same rule as we considered in case of double integration. So here you can see clearly that integration of z is from h1 to h2 and the inputs of these functions h1 and h2 are x, y. That means while taking innermost integration with respect to z, my outer variables x and y are constant. Then if I switch to the second or the middle integral, then it is with respect to y and the limits are in terms of outer variables, which is x. Now remember, at any moment the limits can be constant also, but if the variables are included, they must be outer variables. Coming to the last part, outermost variable which is x, here limits must be constant. So they are from a to b. This is how the formation of triple integration is considered. And the rules are same. There are 3 thumbnails to solve any triple integration or double integration. The first rule is, whenever you are considering inner integration, all outer variables are constant. Second rule is, if you are considering limits of integration, they are always in terms of outer variables or constant. And the final rule is, the limits of outermost variable must be constant. If you remember these 3 rules, you won't get difficulty in any example of multiple integration. So this is how we can consider the structure of 3-dimensional integration. Now let us switch to the second part, which is how to solve actually this triple integration. Suppose I consider some specific limits of variable and if I consider some value of the function, how actually we can go for the calculation, what are the rules of calculation and how to figure out the final answer. So for that reason, let me consider one example, which is triple integration over function x, y, z, and the order is given over here, dz, dy, dx. The limits are 0 to y, 0 to x, 0 to 2, correspondingly for x, y, z, y and x. So the first step is always to give the details to the integration. Which variable is the innermost variable? It will be the limits for innermost integration. And likewise you can go up to the outermost integration. So once I fix this, I need to focus only on the innermost integration, which is here highlighted by orange color. So right now I am taking integration with respect to z, and so for that reason y and x will remain constant throughout this calculation. So you can see clearly it is z square by 2, I am taking limits 0 to y, switching the values, ultimately it will give you x y cube by 2, and 2 is the constant, we can shift it outside the integration. Now at the end of first integration, now while taking the second integration, you can see clearly that as it is with respect to y, highlighting it here by purple color, now I am keeping x constant. So keep x constant, integrate with respect to y, it will give you x y raised to 4 upon 4 and 0 to x are the limits. Ultimately you can take that 4 in the denominator outside the integration, so it will give you x raised to 5. And finally you integrate it with respect to x, it will give you answer 4 by 3. This is how we are going for the calculation of triple integration. It is almost similar to double integration, the only thing is there is one additional integration also. So this is the reason why we are keeping almost every time dz, dy, dx or dz, dx, dy the order of integration. So whenever you will solve the innermost integration, you can switch to the examples of double integration. Okay, now let us come to the third and the main part of this, that is graphical interpretation. How actually this integration is working, how actually it is covering the full domain of the function, and where actually it will transform the value. So considering one example for this construction, I am taking a surface which is z equal to x square plus y square. So it is a paraboloid. I am taking a parabola x square plus y square and then I am rotating it through z axis. So remember here, the red axis is x, green axis is y, and blue axis is z. So I am taking first of all paraboloid x square plus y square. I am considering another paraboloid 3 minus x square plus y square, which is upside down, and I want to find what will be the volume of a solid which is obtained by considering this two surface at a time. So you can see roughly I can say a egg shape of the structure is generated by intersection of these two. You can see clearly egg shape is generated. So this is the case where you want to find the volume which is not resting on the xy plane. In the double integration we have that strength to find the volume of the function, but if there is intersection with xy plane, but here you can see this solid is barely touching the xy plane at one point, which is origin. So that means now we are going for the general perspective of finding the volume. So now how to find this volume? Now if you look carefully, there is intersection of this two paraboloid on a circle which is actually x square plus y square equal to 3 by 2. We'll see later on how to find this intersection also. Now I am moving towards finding the volume of this structure. Now if at this point I recall how actually we were finding the volume of solid using double integration, we were considering the height by the surface, and in region we are considering horizontal or vertical cut. So for that we are considering one axis at a time, and then we are moving in the axis keeping another variable fixed. So here also I am keeping x and y coordinates fixed. My innermost variable is z. This is the reason why change is happening only in z coordinate. You can see clearly I am fixing point in the domain first of all, and this point is exactly 0.5, 0.5, and then if I move my point on this line which is actually change in z coordinate where x and y they are fixed. So what will happen? It will trace a hole in the solid. You will find a line which will trace hole in the solid. You can see this yellow point is moving inside that egg shaped structure and it is creating a line. So my first step is, or my innermost integration is always concentrated on finding this single line. Once this line is obtained, I will take its movement parallel to another axis. So it will give me a plane. So my first construction with respect to z is nothing but value of this line. So at the end of this full momentum or this full change of point from z equal to the minimum value to maximum value, that means from the blue parabola to the pink parabola, it will give you the line. Now the second step is I will change this line parallel to y-axis. So as I know that x is represented by red color, that means now I will move parallel to green axis. So y is changing, x is remaining fixed. So you can see clearly I am constructing all such possible lines from the solid which is moving parallel to y-axis. So y is changing now. So this is talk about second integration. Once you have that inner integration, you have that line. Now you are coming to the second integration which is with respect to y. So y is changing, it will create the plane, and that plane is obtained by this particular phenomena. You can see my line is changing on the solid which is parallel to green coordinate axis, which is nothing but y coordinate. So ultimately it will trace a plane, or you can say that I am cutting that egg-shaped structure parallel to y-axis at some particular point Here I fixed the point 0.5, 0.5. So this is cross section of the solid at length x equal to 0.5. So you can see clearly by this beautiful graphics that there is a cross section which is happening to the solid which is parallel to y-axis, and now it will cover that line also which we considered previously. So this will be the shape. This is nothing but the section of that egg-shaped structure which is happening parallel to y-axis. Let us complete this graphics first, so it will help you to imagine that what actually we are going to consider by this second integration in triple integration. Okay, so now we are done with this. You can see clearly that it creates a plane which is actually crossing your object at some value which is fixed for x and which is changing in y. And that means if you look carefully, if I draw the parabola, it will give me the clear idea that how actually it is crossing, or at which mathematical curve it is crossing my solid. Now what I want to know is what will happen if I move this plane on x-axis. So that means my integration with respect to x, which was remaining as the last variable, is nothing but considering all such planes on the three-dimensional egg-shaped structure. So it will cover the whole volume. This will make more clear about the idea. Now see, these are all parabolas, and you can see the lower part of the egg-shaped structure is covered by blue parabola and the upper part is considered by red. So the first or the innermost integration was about a straight line which is given by this purple color frame. The second integration was actually how we are moving that line parallel to y, that was for dy, and the last is represented in this graphics which is moving parallel to x. So you can see clearly movement in z, my height is changing, movement in y, my length is changing, and then movement in x, and that means my breadth is changing. So this is how you are considering the full construction of volume. And that means if I consider my function's value f of x, y, z, it will take input from this egg-shaped structure and it will transform it somewhere which is in a four-dimensional space. So we are using the word volume. Actually it is in a hyperspace, and so the volume over there is known as hypervolume. But now, if I consider value of the function equal to 1 by using the mathematics of multiplicative identity, I can find the volume of that egg-shaped structure. So it will help me a lot to consider a region or the domain which is not resting on the xy plane and which is randomly lifted on the three-dimensional space. So this consideration is all about finding volume of that egg-shaped structure. So my question is, what will be the volume of a region D which is enclosed by z equal to x square plus y square, z equal to 3 minus x square minus y square. So in the volume of this, let me consider first of all value of z. So now right at this moment I am focusing on z, so my value of z is changing, and therefore I need to start from the surface x square plus y square and I need to end on 3 minus x square plus y square. So the lowermost value of z in this change is on this CN or the sky blue surface, and the uppermost point is on that pink surface. And so the values of z are x square plus y square 2, 3 minus x square minus y square. Now to consider that plane which was moving parallel to y-axis, I am considering the projection of that ring which is nothing but the intersection of this 2 in xy plane. So it will be easy for me to now transform my question into xy plane. So now you can imagine the solid is lying in 3D, I am considering only its projection. This will help me to find value of y. And see, this is the plane which was generated. A plane which was at height 0.5, 0.5, and then I am considering any random plane as we need to take any random cut. So if you look carefully in this is nothing but the circle x square plus y square equal to 3 by 2, and that same circle is coming as a projection of our main circle which is on the solid as intersection of two surface. So here the value of y, which is minimum value of y to maximum value of y, it is nothing but from this circle. Now I am taking the top view of the solid, so it gives you the value of y as root of 3 by 2 minus x square with negative to positive. We are moving from negative side to positive side. And once we have this cut, we know how to move it parallel to x-axis. So this is how you are covering the full solid or the full domain D. So the value of x is coming by the lower and the upper values of the x coordinate occupied by this domain D. So it is minus 1.5 to 1.5. And finally, once we have the formulation of this thing, what I can do, I can come to my regular calculation. I am focusing first on z. So now I have 3 minus 2x square minus 2y square, considering value of y, and again integrating it, it gives me values of, I am using the function's even nature to reduce the limit from minus to plus by multiplying it by 2. And at this point you can see now I can assume polar forms of x and y, x with help of r and theta. So this is how you can mix the values of polar form in between any example of double or triple integration. Here particularly, as we know that we are moving on a circular boundary, it is always advisable to switch to the polar coordinates. So I am taking assumption x equal to root 1.5 sin theta, correspondingly value of dx root 1.5 cos theta d theta, and changing the values of limit from 0 to root 1.5 to 0 to pi by 2. Considering all these inputs into my integration and then expanding this bracket, multiplying it by root 1 by 2 cos theta, ultimately by using the Wallis formula, here I am using the Wallis formula to solve this integration, and that formula is also discussed in our previous talk. So finally it will result into 9 pi by 4. This is nothing but the volume of that egg-shaped structure which was obtained by intersection of two parabolas. So I hope this part is clear now, that how to find volume of any solid using triple integration by considering functions value equal to 1. Also how to formulate triple integration. What do we mean by triple integration graphically? And what actually we are receiving by triple integration if we are considering functions value which is non-zero. It will give you a hyper volume as it is a volume in the hyperspace. So this is all about triple integration. In next talk we are going to discuss how to find triple integration with respect to change of variable. As we consider double integration from Cartesian to polar, in next talk we are going to discuss how to change Cartesian to cylindrical or Cartesian to spherical coordinates. Thank you.
LJ Institute of Engineering and Technology.